Every equation in physics has time in it. Every single one. The Schrödinger equation, the most important equation in quantum mechanics, has a time derivative sitting right there on the left side of the equal sign. IH bar, partial psi, partial t, time. It is in the notation, it is in the structure, it is in the bones of the thing. Newton's laws have time, Maxwell's equations have time, Einstein's field equations have time, the Standard Model has time. Every equation that has ever successfully described the behavior of the physical universe treats time as a given, as a background parameter, as the stage on which everything happens. The equations take a state of the universe at one moment, and they tell you what the state will be at the next moment. That is what physics does. That is what physics is. And then there is the one equation that does not. There is one equation in physics, a single equation that is supposed to be more fundamental than all the others. The equation that describes not a particle, not an atom, not a field, but the quantum state of the entire universe. Everything that exists, everything that has ever existed, everything that could ever exist, all encoded in one wave function, governed by one equation. And when you write that equation down, when you follow the rules of physics carefully and honestly and apply quantum mechanics to the whole of reality, time vanishes. Not approximately, not in some limiting case, completely. The equation has no time in it, because general relativity, when you quantize it properly, eliminates time as a mathematical necessity. The variable simply does not appear. It was never there. The equation is called the Wheeler-DeWitt equation. It looks like this. H hat psi equals 0. And what it says, translated from the math into something you can feel in your chest, is that the universe does not evolve. Nothing changes. Nothing has ever changed. The total quantum state of reality is frozen, static, fixed. The equal sign points to 0, and 0 does not move. This equation has existed since 1967. It has been published, checked, rechecked, argued about, attacked, defended, and reformulated for nearly 60 years. And the people who understand it best, the people who work on quantum gravity for a living, have spent those 6 decades trying to reconcile what the equation says with the fact that you are sitting here, right now, experiencing what certainly feels like the passage of time. Because you are. You feel it. You feel seconds ticking past. You feel the video progressing. You feel yourself getting older while you listen to this. And the equation that is supposed to describe the quantum state of the entire universe says none of that is happening. That is not speculation. That is what the math says. And the man who derived it hated it so much that he spent the rest of his life calling it that damned equation. His name was Bryce Seligman DeWitt, born January 8th, 1923, in Dinuba, California, a small farming town in the San Joaquin Valley. Died September 23rd, 2004, in Austin, Texas, of pancreatic cancer. At the age of 81, DeWitt was a physicist of extraordinary range. He had worked on the Manhattan Project. He had made fundamental contributions to the quantization of gravity, to the theory of quantum fields in curved spacetime, and to the many worlds interpretation of quantum mechanics, which he did more than anyone to popularize. His September 1970 article in Physics Today, titled Quantum Mechanics and Reality, was the piece that introduced Hugh Everett's relative state formulation to the wider physics community. It contained the line that would define the many worlds interpretation for a generation. Our universe must be viewed as constantly splitting into a stupendous number of branches. That was DeWitt. He was not a man who avoided radical conclusions, and yet the equation that bears his name is one he never fully accepted, because the equation did not come from a laboratory or a conference or a blackboard in some ivy-covered building. It came from a phone call at an airport, and from the moment it appeared, DeWitt sensed that it was telling him something he did not want to hear. It was 1965. John Archibald Wheeler, one of the most important physicists of the 20th century, the man who coined the term black hole, the man who supervised Richard Feynman's dissertation, was stuck on a 2-hour layover at Raleigh-Durham International Airport in North Carolina. Wheeler phoned DeWitt, who at the time was running the Institute of Field Physics at the University of North Carolina at Chapel Hill, just a short drive away, and asked him to come keep him company between flights. DeWitt drove to the airport carrying a copy of a paper by the Israeli physicist Asher Perez, a recently published Hamilton-Jacobi formulation of general relativity from the journal Nuovo Cemento. And somewhere between the terminal seats and the flight announcements, in one of those conversations that changes the direction of an entire field, DeWitt mumbled an idea. What if you did the same thing Schrödinger did for the hydrogen atom back in 1926? Take the classical equation, replace the derivatives with quantum operators. See what comes out. Wheeler got tremendously excited. He was often enthusiastic. According to Cecile de Witt-Moret's memoir, The Pursuit of Quantum Gravity, published by Springer in 2011, Wheeler practically levitated on the spot. He declared that the equation for quantum gravity had been found. DeWitt was more cautious. He had learned, over years of working at the boundary of known physics, that enthusiasm and truth are not the same thing. He went home to Chapel Hill and worked through the mathematics carefully. And what came out the other end was an equation that should not exist. I want to walk through why it should not exist, because the technical detail matters here. It is not a footnote. It is the whole story. Compare the two equations side by side. The Schrödinger equation says I h bar times the partial derivative of psi with respect to t equals h hat psi. Look at the left side. See the t. Time is right there, explicit, undeniable. The equation is a machine that takes the quantum state at one moment and tells you what the quantum state will be at the next moment. It is a clock. It ticks. The universe, according to this equation, evolves. Now look at the Wheeler-DeWitt equation. H hat psi equals 0. There is no left side. There is no time derivative. There is no t anywhere. The equation says the Hamiltonian operator acting on the wave function of the universe equals 0. Not equals something that changes. Not equals a function of time. Equals 0. Static. Frozen. Done. The wave function of the entire universe just sits there. It does not tick. It does not evolve. It does not go anywhere. The equal sign points to 0, and 0 is the most motionless number in mathematics. And this was not a mistake. This was not DeWitt forgetting to include a term. This was a direct, unavoidable consequence of applying quantum mechanics to a theory, general relativity, that treats time in a fundamentally different way than every other theory in physics. Here is why, and I want to take the time to explain this properly, because this is where most popular accounts of the Wheeler-DeWitt equation go wrong. They treat the absence of time as some kind of quantum spookiness, some strange artifact of the uncertainty principle, or the wave function, or measurement. It is not. The absence of time in the Wheeler-DeWitt equation is a classical feature of general relativity that gets inherited through the quantization procedure. It has nothing to do with quantum weirdness. It has everything to do with what Einstein built into his theory of gravity in 1915. Einstein's general theory of relativity is what physicists call diffeomorphism invariant. That is a technical term, but the idea behind it is straightforward. In general relativity, the coordinates you use to label points in space-time, the x, the y, the z, and crucially the t, have no physical meaning. They are just labels. You can relabel them however you want, stretch them, compress them, shuffle them around, and the physics does not change. The equations look the same. The predictions are the same. The labels are just bookkeeping. And this applies to the time coordinate too. The t in general relativity is not a clock. It is not measuring anything physical. It is a coordinate label that you are free to change without affecting anything real. In Newtonian physics, time is absolute. There is one clock that ticks for everyone. In special relativity, time is relative, but it is still real, still built into the metric of space-time. In general relativity, the time coordinate is a gauge freedom. It is physically meaningless. Now, when you have a theory where the time coordinate is physically meaningless, something strange happens to the Hamiltonian. In ordinary quantum mechanics, the Hamiltonian is the energy operator. It generates time evolution. It pushes the system forward. It is the engine of change. But in general relativity, because the time coordinate is not physical, the Hamiltonian does not generate time evolution. It generates coordinate transformations. And since coordinate transformations do not change the physics, the Hamiltonian does not change the physics either. It becomes what is called a constraint. Instead of saying, here is how the system evolves, it says, here are the conditions that physically allowed states must satisfy. And the condition is that h hat acting on psi must equal 0. The Hamiltonian is not an engine. It is a filter. And the filter says, only states that do not change are physically real. When you quantize this, when you follow the rules that Paul Dirac laid down for quantizing constrained systems, you get the Wheeler-DeWitt equation. H hat psi equals 0. Time was not lost in the quantization. Time was already gone at the classical level. General relativity told us that the time coordinate is meaningless. Quantization just wrote that fact down in the language of wave functions. Wheeler wanted to call it the Einstein-Schrödinger equation. DeWitt called it that damned equation. The name that stuck, the Wheeler-DeWitt equation, was neither of their choices. But the content was inescapable, and DeWitt published it alone in Physical Review, volume 160, pages 1113 through 1148, on August 25, 1967. It was the first of a trilogy of papers he published that year on quantum gravity. Wheeler's companion framework appeared in the proceedings of the Battelle Rencontres, a conference held in Seattle in the summer of 1967. The proceedings were published the following year as a book, edited by Cecile DeWitt and Wheeler himself, by W.A. Benjamin Press. And here is a detail I find telling. When Misner, Thorne, and Wheeler published their landmark textbook, Gravitation, in 1973, over 1,200 pages of the most comprehensive treatment of general relativity ever assembled The book's index contained no entry for Wheeler-DeWitt, the equation that would become the central equation of quantum cosmology was not indexed in the most important general relativity textbook of the 20th century. Wheeler himself was too modest to name it after himself, and DeWitt apparently wanted nothing to do with it. Carlo Rovelli, who is probably the most articulate living physicist working on the problem of time, wrote a retrospective essay in 2015 called The Strange Equation of Quantum Gravity, published in Classical and Quantum Gravity, Volume 32, and he did not sugarcoat the situation. He called the equation strange and full of nasty features. The functional derivatives in it are distributions that cannot be squared without producing infinities. There is no universally agreed scalar product for the space of solutions. Rivers of ink, Rovelli wrote, have been wasted to discuss this issue. And yet, in his verdict, the equation has had a profound and well-deserved influence on fundamental physics. It is the foundation stone of everything that has come after. And what it describes is not some small corner of reality. It describes everything. The wave function in the Wheeler-DeWitt equation, psi, is not the wave function of a particle or an atom or a laboratory. It is the wave function of the entire universe, defined not on ordinary three-dimensional space, but on what Wheeler called superspace, an infinite dimensional landscape in which every point represents a complete three-dimensional geometry of the cosmos. Every possible shape that space could take, every possible curvature, every possible arrangement of matter and energy on every possible background, all of it compressed into a single mathematical object, psi, living in a space with infinitely many dimensions. And the equation says this object does not change. Wheeler described the arena in Harper's Magazine in July 1974. The arena in which space does its changing is not even the space-time of Einstein, he wrote. For space-time is the history of space changing with time. The arena must be a larger object, superspace, endowed with an infinite number of dimensions. He was describing a mathematical space so vast that ordinary space-time, the four-dimensional fabric of reality that Einstein showed us, is just a single point in it, one configuration among infinitely many. And the equation says that the wave function defined on this infinite space does not evolve. It just sits there, a static, frozen function on an infinite dimensional landscape, encoding every possible universe, every possible history, every possible future, all at once, all equally real, all equally present. That is what h hat psi equals 0 means. It means the totality of everything that could ever exist is a fixed mathematical object. And you, and your experience, and your memories, and your sense of time passing are somewhere inside that object, but the object itself does not move. Despite its ugly technical features, the equation is foundational. James Hartle and Stephen Hawking used it as the starting point for their no-boundary proposal in 1983, published in Physical Review D, Volume 28, proposing that the universe has no boundary in time, that the Big Bang is not an edge, but a smooth rounding off like the South Pole of the Earth. Alexander Vilenkin used it for his tunneling cosmology, published in Physics Letters B in 1982. The idea that the universe quantum tunneled into existence from nothing. And Abhay Ashtekar, Lee Smolin, Carlo Rovelli, and Ted Jacobson used it as the seed of loop quantum gravity, showing that space itself might be quantized into discrete atoms of geometry. All of these programs All of these research directions that have occupied hundreds of physicists for decades trace back to the damned equation that DeWitt wrote on the back of his notes after a phone call at an airport. But none of them solve the problem of time, because the problem of time is not a technical obstacle you can engineer your way around. It is a feature of the equation itself, and the equation, for all its nastiness, is the only equation we have. The equation sat there, and for the next 25 years, physicists tried to fix it, because the equation had a problem. Not a mathematical problem, a philosophical one, a human one. The equation said the universe does not evolve. And the universe, from the perspective of every human being who has ever lived, manifestly does evolve. Things change, stars are born and die, people grow old. Ice cream melts. The arrow of time is the most obvious feature of physical reality, and the most fundamental equation in physics says it does not exist. This disconnect, this gap between what the equation says and what you experience every second of your life, is called the problem of time in quantum gravity, and it fractured the field. Karel Kuchař, a Czech-born physicist who spent most of his career at the University of Utah, wrote the definitive review of the problem in 1992. It was presented at the 4th Canadian Conference on General Relativity and Relativistic Astrophysics, and later reprinted in the International Journal of Modern Physics, D, in 2011. Kuchař was meticulous. He catalogued 10 distinct approaches that physicists had proposed to recover time from the timeless equation. 10 different strategies built by some of the sharpest minds in theoretical physics over 25 years. And for each approach, Kuchař showed how it failed. Not partially, not with caveats, failed. Each approach would solve the problem in one place and reintroduce it somewhere else. Kuchař summarized his conclusion with a Czech proverb that became famous in the quantum gravity community. The devil thrown out of the door returns through a window. Chris Isham at Imperial College London wrote a parallel review the same year, published as a preprint on the Arxiv. Isham partitioned all existing approaches into 3 categories. Category 1, you try to identify time before you quantize the theory. Category 2, you try to extract time from the quantum theory after quantization. Category 3, you accept that there is no time at all. And the most unsettling thing about the state of the field in 1992, 3 decades after the equation was first written down, was that a growing number of serious, credentialed, published physicists were choosing option 3. Time is not missing from the equation because we made a mistake. Time is missing because it is not real. The equation is correct. And your experience of time, the most intimate and seemingly undeniable feature of your conscious life, is the thing that needs explaining. I want to stop here for a moment and talk about a misconception, because there is a version of this story that you might have heard, a version that makes the problem seem less alarming than it actually is. The version goes like this: the problem of time is a technical issue. We have not yet figured out how to combine quantum mechanics and general relativity into a complete theory, and when we do, time will reappear. The absence of time in the Wheeler-DeWitt equation is just a sign that the equation is incomplete, or approximate, or wrong in some subtle way that a better theory will fix. That is not what the problem of time is. The problem of time is not a technical obstacle. It is a message. The math is not confused. The math is perfectly clear. When you take general relativity seriously, when you take its deepest feature, diffeomorphism invariance, and follow it honestly into the quantum domain, time disappears, not as an artifact of our ignorance, as a consequence of the structure of the theory. Every attempt to put time back in has failed. Kuchař showed this. 10 approaches, 10 failures. The devil keeps coming back through the window, and the reason it keeps coming back is that you cannot put time back into a theory that was designed from the ground up to not have it. General relativity is a theory in which the time coordinate is not real. Quantizing it faithfully preserves that feature. The Wheeler-DeWitt equation is not broken. It is honest. And this is where I think the popular science accounts do the most damage. They frame the problem of time as if it is like the Higgs boson before 2012, a missing piece, a gap in the puzzle that some clever theorist or some enormous collider will eventually fill. But it is not like that. The problem of time is more like the measurement problem in quantum mechanics. It is not a gap, it is a feature. It is the theory telling you something about reality that conflicts with your everyday experience. And the conflict is not a sign that the theory is wrong. The conflict is the point. Think about it this way. Every morning, you wake up and the sun appears to rise. It moves across the sky. It sets in the west. Your eyes tell you, clearly and unmistakably, that the sun orbits the earth. And yet you know, because Copernicus and Kepler and Galileo showed you, that the sun is not moving. You are. Your experience of the sun rising is real, in the sense that you really do experience it. But it does not correspond to what is actually happening. The rotation of the earth creates an illusion of solar motion that is indistinguishable from inside the experience from actual solar motion. The Wheeler-DeWitt equation is saying the same thing about time. Your experience of time passing is real in the sense that you really do experience it, but it may not correspond to what is actually happening at the deepest level of physics. The entanglement between you and the rest of the universe creates an illusion of temporal flow that is indistinguishable from inside the experience, from actual temporal flow. And just as there is no experiment you can perform from the surface of the earth that will make the sun's apparent motion feel less real, there is no experiment you can perform from inside the universe that will make the passage of time feel less real. The illusion is perfect, and it may be all there is. And the person who saw this most clearly, who argued for this conclusion most persistently and most radically for more than half a century, was not sitting in a department at Harvard or Cambridge or the Institute for Advanced Study. He was sitting in a farmhouse. Julian Barbour was born on February 13th, 1937. Not in England, as many biographical summaries incorrectly state, but in Jerusalem, in what was then mandatory Palestine. His parents were English, David Neville Barbour and Violet Mary Barbour. He was raised in South Newington, a village in Oxfordshire with a population of a few hundred people, a 12th century Norman church dedicated to St. Peter ad Vincula, and not much else. He went to Cambridge, where he studied mathematics and earned what he later described, with characteristic British understatement, as a rather ordinary second-class degree. He spent a year in Munich, improving his German, attending a language school that he later discovered had been run by the man who served as Adolf Hitler's chief interpreter during the war. And he completed his doctorate at the University of Cologne in 1968, writing his thesis on the foundations of general relativity. The pivotal moment of his life, the moment that set the course of the next 6 decades, happened on October 18th, 1963. He was 26 years old. He was on a train in Bavaria heading south to climb the Watzmann, which at 2,713 meters is the third highest peak in Germany. He was reading a newspaper that contained a summary of an article Paul Dirac had recently published in Scientific American, questioning the four-dimensional symmetries of physics. Something in that summary lodged in Barbour's mind. That night, in a mountain hut, he barely slept. He woke with a splitting headache and told his climbing partner something that would have seemed absurd to anyone who overheard it. "You will have to go up the mountain on your own." And while his friend climbed the Watzmann, Julian Barbour sat alone in the hut and asked a question that would consume the rest of his life. What is time? 58 years later, in a Nautilus profile published in May 2021 by the science journalist Michael Brooks, Barbour admitted something remarkable about that morning. "There's not a word about Dirac asking what time is," he said. "I must have invented that to give myself the confidence to challenge this thing." He had manufactured a permission slip. He had attributed his own question to one of the most revered physicists in history, given himself the cover of authority, and then spent the rest of his life answering a question that Dirac never actually asked. Whether that is self-deception or genius is a question I still do not know how to answer. What happened next is the part that should make you angry, because Barbour's answer to the question of time turned out to be correct, or at the very least, it turned out to be consistent with the deepest equation in physics, supported by experimental evidence and endorsed by several of the most prominent theoretical physicists alive. And he did all of it from outside the system. After his doctorate, Barbour met Felix Pirani at King's College London. Pirani told him that a career in academic physics required 2 solid research papers a year. The prospect, Barbour told Physics World in a 1999 interview with the editor Matin Durrani, horrified him. He did not want to be on a treadmill. He did not want to produce incremental papers on a schedule dictated by tenure committees and grant cycles. He wanted to think about one question, the deepest question, for as long as it took. And so he made a decision that almost no physicist in the modern era has made. He walked away from academia entirely. In November 1963, just weeks after the morning on the Watzmann, Barbour bought College Farm in South Newington, a 360-year-old stone house tucked against the wall of the Norman church, purchased with money his father gave him to avoid death duties. And from 1969 to 1997, for nearly 30 years, Julian Barbour paid his bills by translating Russian scientific journals into English for Plenum Publishing and the American Institute of Physics. He told Michael Brooks that he could churn out 50 to 60 pages of theoretical physics translation a day and was basically earning a professorial salary doing it. Not having to apply for grants was absolute bliss, he said. He spent 5 weeks each spring and summer visiting Bruno Bertotti at the University of Pavia in Italy, collaborating on the physics he could not work on full-time because he had chosen freedom over funding. "I liken myself to a bee going to get nectar from academia," he told Brooks. "I want you to sit with that image, a man in a farmhouse in the English countryside, surrounded by sheep and stone walls, and a church that has been standing since the 1200s, spending his mornings translating Russian physics papers to earn a living, and his afternoons working alone on the question that the entire international community of quantum gravity researchers could not answer. No office, no students, no departmental meetings, no tenure review, no pressure to publish anything he did not believe was right. Just a man and a question for 30 years. And the institutional physics community did not know what to do with him. He was not a crank. His mathematics was rigorous. His papers were published in the best journals. Roger Penrose engaged with his work. Wheeler endorsed his book, but he was not one of them. He did not sit on grant committees. He did not supervise doctoral students. He did not attend the right conferences at the right times, or schmooze with the right editors, or position his work within the right fashionable research programs. He was, in the most literal sense, an outsider. And the question he was working on, the question of whether time is real, was itself an outsider question. It was the kind of question that tenured professors at serious universities would discuss over drinks at a conference dinner, but would never put at the center of a grant proposal. Too philosophical, too risky, too likely to lead nowhere publishable. The career incentive structure of academic physics is designed to reward incremental progress on well-defined problems, not decades-long meditation on questions that might not have answers. Barbour's decision to leave academia was not just a personal choice. It was a structural necessity. The question he needed to ask could not be asked from inside the system. And his answer to the question was the simplest and most radical answer possible. Time does not exist. That is not a philosophical position. That is not a meditation practice. That is what the equation says. The Wheeler-DeWitt equation has no time in it because there is no time. What exists, Barbour argued, is an infinite dimensional configuration space that he called Platonia, after the philosopher who first proposed that the truest form of reality is timeless and unchanging. Platonia is the space of all possible arrangements of the universe. Every possible configuration of every particle, every field, every geometry, all laid out simultaneously in a vast mathematical landscape. Each point in Platonia is a now, a frozen snapshot of a possible state of the universe. And what you experience as the flow of time is not the universe moving from one now to the next. There is no movement, there is no flow. What you experience is the structure of certain nows that happen to contain what Barbour called time capsules, configurations that look like records of a past. Your memories are not recordings of events that happened. They are features of the particular now you occupy right now. The past is not behind you. It is inside you. And it was never past. His 1982 paper with Bruno Bertotti, Mach's Principle and the Structure of Dynamical Theories, published in the Proceedings of the Royal Society A, Volume 382, page 295, was the mathematical foundation. It reformulated Newtonian dynamics in purely relational terms, without any reference to absolute space or absolute time. Simon Saunders, reviewing the work, called it a solution to a problem Newton thought insurmountable, and Einstein failed to resolve. And in 1999 came the book, The End of Time, The Next Revolution in Physics, published by Weidenfeld and Nicholson in the United Kingdom and by Oxford University Press in the United States. Wheeler himself, co-creator of the damned equation, supplied a blurb for the jacket. Plato and Aristotle, if they had read it, would still be discussing it. The book won the Association of American Publishers 2000 prize for excellence in physics and astronomy. But Barbour's argument, as radical and elegant as it was, had a gap. He could show you that the equations were consistent with a timeless universe. He could argue philosophically that time is an illusion, but he could not show you the mechanism. He could not point to the specific physical process that generates the illusion of temporal flow from a frozen mathematical structure. He could tell you that time does not exist. He could not tell you why it feels like it does. And here is where the story takes a turn that nobody could have predicted. Because 14 years before Barbour's book was published, and 18 years after DeWitt's airport epiphany, two physicists had already proposed the mechanism. They had published it in one of the most prestigious physics journals in the world, and then the entire field had ignored it for 30 years. Their names were Don Page and William Wootters. Don Nelson Page was born December 31st, 1948. He earned his PhD at Caltech in 1976, supervised jointly by Kip Thorne and Stephen Hawking. He is an evangelical Christian. He lived with the Hawking family in Cambridge during his postdoctoral years. In a 2018 interview with CBC Radio's Quirks and Quarks, Page recounted reading his Bible to Stephen Hawking at breakfast. When Page told Hawking the story from Mark chapter 5 about Jesus casting evil spirits into a herd of swine that then drowned themselves in the Sea of Galilee, Hawking replied that the Royal Society for the Prevention of Cruelty to Animals would not like that story. Think about that pairing, a deeply religious man and one of the most famous atheists in the history of science, eating breakfast together every morning, arguing about swine and salvation, and in their professional hours, working on the physics of black holes and the nature of time. The personal and the scientific are not separate threads. They are the same thread. William Kent Wootters earned his undergraduate degree at Stanford in 1973 and his doctorate at UT Austin in 1980. He eventually became the Barclay Germain Professor of Natural Philosophy at Williams College, a position he held until his retirement in 2017. Wootters is one of the founders of quantum information theory. With Wojciech Zurek, he proved the quantum no-cloning theorem in a paper published in Nature on October 28, 1982, volume 299, page 802. And in a 1992 conversation with Benjamin Schumacher, Wootters coined the word qubit, the fundamental unit of quantum information, a term that is now used thousands of times a day in physics laboratories around the world. These were not fringe figures. These were serious physicists with impeccable credentials. And in 1983, they published a paper that should have changed the direction of the entire field. It did not because it was wrong, because it was too uncomfortable. The paper was titled Evolution Without Evolution, Dynamics, Described by Stationary Observables. Physical Review D, Volume 27, pages 2885 through 2892, published June 15, 1983, received by the journal on June 17, 1982, written at the University of Texas at Austin. And the argument it contained is, in my estimation, one of the most elegant ideas in the history of theoretical physics. Here is what they proposed. Take the universe, all of it, and split it conceptually into two parts. One part is a clock, any physical system that can serve as a clock. The other part is everything else, everything that is not the clock. Now write down the total quantum state of both parts together, the clock and the rest, combined into a single wave function, and demand that this total state obeys the Wheeler-DeWitt equation. H hat psi equals 0. The total state is frozen, static, timeless, nothing evolves. But now ask a different question. Instead of asking what the total state looks like, ask what the rest of the universe looks like given that the clock reads a particular value. Condition on the clock. Project the total state onto a specific clock reading. And when you do this, when you perform this conditional operation, something extraordinary falls out of the mathematics. The conditional state of the rest of the universe, the state you see when you look at the system through the lens of a particular clock reading, satisfies the ordinary Schrödinger equation. It evolves. It changes. It flows. Time appears, not as a fundamental parameter, as a correlation. The total state is frozen, but the relationship between the clock and the rest of the universe is not frozen. The correlations between them are structured in exactly the way that a time-evolving system would look if you could trace out its history. And those correlations are entanglement. The clock is entangled with everything else. The entanglement pattern encodes what looks, from inside the system, like the passage of time. But from outside, from the perspective of the total quantum state, nothing has changed. Nothing has ever changed. I need to pause here because I want to make sure the full weight of this lands properly. What Page and Wootters were proposing is not a metaphor. It is not an analogy. It is a mathematical result. They were saying that time is not a background parameter that the universe moves through. Time is not a stage on which events are performed. Time is not a river or an arrow or a dimension. Time is a quantum correlation between subsystems of a static universe. It is not something the universe does. It is something the universe is. The flow you feel, the sensation of one moment giving way to the next, is not the universe evolving. It is you, a subsystem, being entangled with a clock, another subsystem. And the entanglement between you and the clock looks, from your perspective, from inside the entanglement, exactly like time passing. But from the perspective of the total quantum state, the wave function of the universe, nothing is happening. Nothing has ever happened. The equal sign still points to 0. Let me make this concrete. Right now, as you are listening to this, your brain is processing information. Neurons are firing. Electrochemical signals are propagating along axons, crossing synaptic clefts, activating downstream neurons. You are having thoughts. You are forming memories. You are experiencing what feels like a continuous flow of conscious experience, a river of awareness carrying you from one moment to the next. And according to the Page-Wootters mechanism, all of that, every thought, every signal, every firing neuron, is a correlation. Your brain state at this moment is entangled with the state of the clock on your wall, the position of the Earth in its orbit, the vibration of the cesium atoms in the atomic clock at the National Institute of Standards and Technology in Boulder, Colorado. All of these things are correlated with each other, and the pattern of correlations is structured in exactly the way that a time-evolving system would look. But the total state, the state of all of these things taken together, does not evolve. It cannot evolve. The equation says so. Your memories of the beginning of this video are not records of something that happened in the past. They are features of the particular correlation pattern you are embedded in right now. The past is not a place you came from. It is a direction in the space of correlations. And the future is not a place you are going to. It is another direction. And both directions are already there, encoded in the static wave function, waiting for an internal observer, which is what you are. to read the correlations and experience them as a sequence. Time is not a river you are floating down. Time is a relationship you are trapped inside, and you cannot step outside the relationship to check whether the river is real, because stepping outside would require you to stop being a subsystem of the universe. And you cannot do that because you are made of the universe. You are part of the entanglement. You are inside the equation. Wootters extended the idea the following year in a paper titled Time Replaced by Quantum Correlations, published in the International Journal of Theoretical Physics, Volume 23, page 701, in August 1984. The title alone tells you everything. Time replaced, not supplemented, not reinterpreted, replaced. And then the field ignored them for 30 years. I want to stay with this for a moment because the pattern matters. Page and Wootters published one of the most conceptually profound papers in the history of quantum gravity. They proposed a specific, testable mechanism by which the illusion of time could arise from a timeless quantum state. The math was clean. The logic was sound. The paper appeared in Physical Review D, one of the 2 or 3 most prestigious physics journals in the world. And the response of the physics community was to find technical objections and then move on. Karel Kuchař, the same meticulous Czech physicist who had catalogued 10 failed approaches to the problem of time, delivered what the physicist Charles Dolby later called a reductio ad absurdum of the Page-Wootters mechanism. Kuchař showed that when you applied the conditional probability approach to a relativistic particle, you got the wrong localization probabilities. You got the wrong 2-time correlations. You got ambiguous propagators. The technical objections were serious and specific. They were not hand-waving. They were mathematical demonstrations that the Page-Wootters mechanism, as originally formulated, gave incorrect predictions in certain regimes. But here is the thing about the technical objections. They turned out to be fixable, every single one of them. It took 30 years, but by 2021, every objection Kuchař raised had been answered. The mechanism was not wrong. It was incomplete. And the difference between wrong and incomplete is the difference between a dead end and a road that needs more work. The physics community treated it as a dead end because dead ends are easier. Dead ends mean you can stop thinking about the uncomfortable implications and go back to working on something else, something safer, something more likely to generate the 2 papers a year that Felix Pirani told Julian Barbour he would need. And this is why you have never heard of the Page-Wootters mechanism, not because it is obscure or technical or irrelevant, because the implication, the idea that your experience of time is a quantum correlation rather than a feature of reality, is so uncomfortable that the field would rather file the paper away than follow the thread. The reason you were never told this is not that it was disproven, it is that the implication was too uncomfortable. And so the paper was shelved, not retracted, not disproven. Shelved, put in a drawer, and left there while the field moved on to other approaches, other frameworks, other ways of avoiding the fact that the most fundamental equation in physics has no time in it. The revival began slowly, almost reluctantly, in 2009. Rodolfo Gambini, Rafael Porto, and Jorge Poulin published a paper in Physical Review D, Volume 79, arguing that Kuchař's objections could be answered by restricting the analysis to a specific class of observables called Dirac observables. In 2015, Vittorio Giovanetti, Seth Lloyd, and Lorenzo Marconi gave a modernized reformulation in Physical Review D, volume 92. In 2017, Chiara Marletto and Vlatko Vedrell at Oxford published a paper in Physical Review D, volume 95, titled Evolution Without Evolution and Without Ambiguities, claiming that the mathematical ambiguities in the original Page-Wootters approach had been fully resolved. And in 2021, Philip Hone, Alexander Smith, and Maximilian Locke published what they called the Trinity of Relational Quantum Dynamics in Physical Review D, volume 104, which unified the Page-Wootters approach with two other frameworks and showed that they are all mathematically equivalent. 30 years of the mechanism sitting in a drawer, 30 years of the field treating it as a curiosity rather than a clue. 30 years during which the most elegant resolution of the problem of time gathered dust because Kuchař had found technical objections that turned out to be fixable. But the revival was not just theoretical, because while the theorists were arguing about Dirac observables and propagator ambiguities, an experimental team in Italy had already done something remarkable. They had built the mechanism in a laboratory. They had tested it with photons, and it worked. The Istituto Nazionale di Ricerca Metrologica sits on the Strada delle Cacce in Turin. It is Italy's National Metrology Institute, the place where they calibrate the instruments that measure the instruments that measure reality. It is one of the most precise measurement laboratories in Europe. And in 2013, a team led by Ekaterina Moreva, working with Marco Genovese, Giorgio Breda, Marco Gramegna from INRIM, Vittorio Giovannetti from the Scuola Normale Superiore in Pisa, and Lorenzo Marconi from the University of Pavia, built a tabletop experiment that demonstrated the Page-Wootters mechanism with entangled photons. The paper was titled Time from Quantum Entanglement, an experimental illustration. It was posted to the arXiv on October 17, 2013, and published in Physical Review A, volume 89, article 052122 on May 20, 2014. And it opened with a quote from Augustine of Hippo from Book 11 of the Confessions, written in approximately 397 AD. Quid est ergo tempus, si nemo ex me querat scio, si querenti explicare velim nescio. What then is time? If no one asks me, I know. But if I wish to explain it to one who asks, I know not. 1600 years between the question and the experiment said Augustine was right to be confused. Here is what they built. And the experimental detail matters, because this is where the idea stops being philosophy and starts being physics. They used a process called Type 1 spontaneous parametric down conversion. 2 beta barium borate crystals, oriented at right angles to each other, pumped by a 700 milliwatt argon ion laser. When a photon from the laser hits the crystals, it has a small probability of spontaneously splitting into 2 lower energy photons called signal and idler that are quantum mechanically entangled. The entangled photons had a wavelength of 702 nanometers, right at the boundary between visible red and near-infrared, filtered through 1 nanometer bandwidth interference filters to ensure spectral purity. A Thomson prism and a half-wave plate prepared the photon pair in a specific entangled state called the polarization singlet. 1 photon was designated the clock, the other was designated the system. Rotating birefringent quartz plates one 957 micrometers thick and the other 1752 micrometers thick, were placed in the beam paths. These plates rotate the polarization of the photons as they pass through, and the rotation angle depends on the plate thickness and orientation. The rotation acts like a Hamiltonian, evolving the photon's polarization state. The plate orientation, which the experimenters rotated through 15 equally spaced angles, played the role of the unobservable coordinate time, the t that appears in the Wheeler-DeWitt equation and has no physical meaning. Then they ran the experiment in two modes. And the two modes are the entire point. In what the paper calls observer mode, they measured the clock photon at a polarizing beam splitter, collapsing it into one of two possible polarization states. These two states represent two clock readings, two times, separated by a specific interval determined by the quartz plate thickness. Think of it this way. The clock photon's polarization is a dial. The dial can point in different directions depending on how the quartz plate has rotated it. Measuring the clock photon at the beam splitter is like reading the dial. You get one of two possible readings, and each reading corresponds to a moment in the internal time of the system. They measured the system photon in coincidence with the clock photon and recorded the results. Then they averaged over all 15 plate orientations to simulate ignorance of the external coordinate time t, the meaningless parameter that the Wheeler-DeWitt equation says has no physical content. What they found was that the conditional probability of finding the system photon in a particular polarization state oscillated sinusoidally with the clock reading. When the clock said time 1, the system photon had a certain probability of being vertically polarized. When the clock said time 2, the probability was different. The system evolved. Time appeared. From the perspective of an observer inside the system, an observer who reads the clock and then looks at the system, the universe was changing from one moment to the next. And the evolution they observed was not random. It was not noise. It was the exact evolution predicted by the ordinary Schrödinger equation, applied to the system photon's polarization state evolving under its Hamiltonian. The internal observer saw standard quantum mechanics unfolding in front of their eyes. Time, as experienced from inside, was indistinguishable from real time. The correlations between the clock and the system were structured in precisely the way you would expect if the system were genuinely evolving in a real fundamental physical time. Then they ran it in super observer mode. And this is the part that should keep you up tonight. This time, instead of measuring the clock photon directly, they sent it through a 50-50 beam splitter. The beam splitter is the key to the entire experiment, and I want to explain why. When a photon hits a 50-50 beam splitter, it has an equal probability of being transmitted or reflected. If the photon was in a definite polarization state before the beam splitter does not destroy that information. But if the photon was carrying timing information, if its polarization was correlated with a specific clock reading, the beam splitter erases that information. It scrambles the witch reading data. It performs a quantum erasure operation that destroys any reference to when the system photon should be observed. After the beam splitter, the clock photon's timing information is gone, and with it goes any reference to time inside the experiment. The experimenters then performed full 2-photon quantum state tomography on both photons together. Tomography is the quantum equivalent of a full body scan. You make thousands of measurements on identically prepared photon pairs measuring different polarization combinations. And from the statistics, you reconstruct the complete quantum state, the density matrix of the two-photon system. It is painstaking, precise, and unambiguous. And what they found was that the fidelity of that total state, the overlap between the measured state and the ideal static entangled singlet state they had prepared, remained constant and close to 1. It did not depend on the plate orientation. It did not depend on the external time parameter t. It did not depend on anything. The total state was the same regardless of what the external coordinate time was doing. The universe, viewed from outside, from the perspective of someone who can see both photons simultaneously without conditioning on the clock, was frozen, static, unchanging, timeless, exactly as the Wheeler-DeWitt equation demands. I want to say that again, because I think the strangeness of it gets lost in the technical detail. The same two photons produced by the same laser passing through the same crystals, measured by the same detectors, yield two completely incompatible descriptions of reality, depending on how you look at them. Look at the pieces conditioned on the clock, and you see a universe that evolves. Look at the whole, erase the clock information, and you see a universe that is frozen. Both descriptions are simultaneously correct. They are not contradictions. They are not approximations. They are two mathematically exact perspectives on the same quantum state, related by entanglement. The universe is evolving and frozen at the same time, and which one you see depends on where you stand. The authors were scrupulously careful. They called the experiment an illustration, not a proof. They explicitly wrote that their setup cannot discriminate between these and other proposed solutions for the problem of time. This was a demonstration with two photons in a lab in Turin, not a measurement of the wave function of the cosmos. They were not claiming to have proven that time does not exist. But what they showed was real. What they showed was that the Page-Wootters mechanism is not just mathematics. It works in the physical world. A static entangled state can simultaneously appear frozen and evolving depending on what you choose to measure. The math was not lying. The mechanism works, and the implications, if you are willing to follow them, go further than most physicists are willing to say in public. Because if you scale the result, if you take the logic of the Turin experiment and apply it not to two photons on a lab bench, but to the universe as a whole, then the implication is this: you are the internal observer. You are the one reading the clock. You are the system photon, entangled with everything around you, experiencing the correlations between your subsystem and the rest of reality as a flow of time that feels as real as anything you have ever known. And the total quantum state of the universe, the state described by the Wheeler-DeWitt equation, is not flowing. It is not changing. It is sitting there, equal to zero, silent and still, while you experience the correlations inside it as the passage of seconds and minutes and years. And there is no super observer. There is no one standing outside the universe running the experiment in the other mode, confirming that the total state is frozen. The universe is a closed system. There is no outside, which means there is no way to check. There is no experiment you can run, no measurement you can perform, no observation you can make. That will tell you definitively whether time is really passing, or whether you are a pattern in a static wave function that merely looks from the inside like it is moving. This is not a gap in our current technology. This is a structural feature of the physics. The question may not have an answer from inside the system, A 2017 follow-up experiment by the same Turin group published in Physical Review D, Volume 96, in November 2017, pushed the result further. They showed that from the internal observer's perspective, the temporal correlations violate a Leggett-Garg inequality, a mathematical test that distinguishes genuinely evolving systems from systems that merely appear to evolve when sampled at multiple times. The internal observer sees genuine dynamics. The external observer sees nothing. Both are looking at the same photons. And in 2021, Foti, Coppo, Barney, Kucholi, and Verrocchi published a paper in Nature Communications, Volume 12, that extended the Page-Wootters mechanism beyond quantum mechanics. They showed that it recovers not just the Schrödinger equation, but Hamilton's equations of motion as well, the backbone of all classical physics. Newton's laws, reformulated as Hamilton's equations, fall out of entanglement with a clock in a timeless universe. Their conclusion was stated with a clarity that I think history will vindicate. There is not a quantum time possibly opposed to a classical one. There is only one time, and it is a manifestation of entanglement. One time. And it is not a thing. It is a correlation, and this result connects to something even deeper. Because the relationship between entanglement and the structure of reality does not stop at time. It extends to space itself. In 2010, Mark van Ramsdonk at the University of British Columbia published a paper that won first prize from the Gravity Research Foundation. The title was Building Up Space-Time with Quantum Entanglement. What van Ramsdonk showed, building on the ADS/CFT correspondence that Juan Maldacena had discovered in 1997, was that if you take two regions of space-time and disentangle the quantum degrees of freedom associated with them, the regions pull apart and pinch off from each other. The spatial connection between them, the geometry that connects point A to point B, weakens and eventually breaks. Space-time is held together by entanglement. Reduce the entanglement and space itself falls apart. In 2013, Maldacena and Leonard Susskind proposed what they called the ER equals EPR conjecture, published in Fortschritte der Physik, Volume 61. ER stands for Einstein-Rosen, the authors of the 1935 paper that described wormholes, tunnels through space-time connecting distant points. EPR stands for Einstein, Podolsky, and Rosen, the authors of the famous 1935 paper on quantum entanglement. And the conjecture says they are the same thing. Every pair of entangled particles is connected by a microscopic wormhole. Every wormhole is a manifestation of entanglement. The geometry of space, the fabric of reality that you move through every day, is quantum correlation made visible. Now, put it together. Space is entanglement. The Page-Wootters mechanism says time is entanglement. The universe, at its deepest level, is not a stage on which events are performed. It is not a container in which things happen. It is a web of quantum correlations. And what you experience as 3 dimensions of space and 1 dimension of time, the 4-dimensional arena that every physics textbook describes as the framework of reality, is the internal view of that web. It is what entanglement looks like when you are made of it and cannot step outside to see the pattern. You are not in space-time. Space-time is in you, or more precisely, space-time is the pattern of your entanglement with everything else, and the equation that describes the totality of all those entanglements says the pattern does not change. And Don Page the evangelical Christian who lived with the Hawkings and co-authored the 1983 paper that everyone ignored, went on to make another contribution that turned out to be just as important. In 1993, Page published a paper in Physical Review Letters, volume 71, page 3743, calculating the rate at which quantum information leaks out of an evaporating black hole. The calculation produced what is now known as the Page curve, a graph showing how the entanglement entropy between a black hole and its radiation changes over the course of the black hole's evaporation. The entanglement starts at 0, rises as the black hole radiates, reaches a maximum at a time now called the Page time, roughly halfway through the evaporation process, and then decreases back to 0 as the black hole finally disappears. The Page curve is now considered one of the most important theoretical results in the physics of black holes. It sits at the center of the black hole information paradox. Recent breakthroughs using quantum extremal surfaces and replica wormholes, published in 2019 and 2020, have confirmed that the Page curve is correct. The same man whose theory of time was shelved for 3 decades produced a calculation that is now considered foundational to one of the most active research areas in theoretical physics. Don Page may be the most important living theorist of the relationship between entanglement and the large-scale structure of reality. His work on the Page-Wootters mechanism says time is entanglement. His work on the Page curve says the fate of information in black holes depends on entanglement. His entire career has been about one thing: how quantum correlations make the universe what it is. And his most important paper was ignored for a generation, not because it was wrong, because the implication was too uncomfortable to absorb. That pattern has repeated itself across the entire history of this problem, and it is repeating itself right now. But not everyone accepted the disappearance of time, and the counter-argument came from an unexpected direction. It came from one of Barbour's closest intellectual allies, a man who had written the friendly blurb on the back cover of The End of Time, and then, a few years later, reversed himself completely. Lee Smolin was born June 6, 1955, in New York City. He is one of the founding faculty members of the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, one of the most influential theoretical physicists of his generation, and a man who has never been afraid of an intellectual fight. His 2006 book, The Trouble with Physics, took aim at string theory and the entire culture of theoretical physics, accusing the field of groupthink, conformity, and an inability to tolerate dissent. He knows what it is like to be an outsider within physics. He and Barbour were natural allies. Both questioned orthodoxy. Both were willing to follow arguments to uncomfortable conclusions. Both were willing to say things that the mainstream would rather not hear. And that is what makes Smolin's reversal so striking, because it was not the reversal of an enemy. It was the reversal of a friend. In 2001, Smolin posted a paper to the Arxiv titled The Present Moment in Quantum Cosmology, Challenges to the Arguments for the Elimination of Time, in which he attacked Barbour, Hawking, and Charles Misner by name. The argument was direct. Dismantling time, Smolin said, is not just wrong. It is dangerous. The timeless picture, the block universe, the frozen wave function, is not merely an alternative interpretation of the physics. It is a capitulation. It is the physics community giving up on understanding the most obvious feature of reality and declaring it an illusion because the equations are more tractable without it. In 2013, Smolin published Time Reborn, a full-length book with the subtitle From the Crisis in Physics to the Future of the Universe, and his argument was the exact mirror of Barbour's. Space may be an illusion, Smolin wrote, but time must be real. Not just real in the sense that we experience it, real in the deepest possible sense, more real than space, more real than the laws of physics themselves. This is a radical claim, and it is worth pausing to understand just how radical it is. Physics has, for 4 centuries, been in the business of discovering timeless laws. Newton's law of gravitation, Maxwell's equations, Einstein's field equations, the Standard Model Lagrangian. These are all structures that are supposed to be eternal, unchanging, written into the fabric of reality from the beginning. The laws do not evolve. The laws do not have a history. The laws simply are. And physicists have always treated this timelessness as a feature, not a bug. The whole point of doing physics, on the traditional view, is to discover the eternal truths that govern the temporal world. Smolin attacked this directly. He argued that even the laws of nature evolve, that the constants of nature are not constant, that the universe is not governed by timeless mathematical truths, but by habits, regularities that emerge through a process he calls cosmological natural selection, first proposed in a 1992 paper in Classical and Quantum Gravity, Volume 9. In this framework, black holes give birth to new universes with slightly varied physical constants, and over deep time, the constants that produce the most black holes, which then produce the most daughter universes, are the constants that come to dominate. The laws of physics are not written in eternity. They are products of a temporal process. Time made them. And if time made the laws, then time is more fundamental than the laws. Time is the one thing that cannot be an illusion, because illusions require a stage on which to perform, and the stage itself is made of time. His subsequent collaboration with the Brazilian philosopher Roberto Mangabeira Unger produced a 566-page volume, The Singular Universe and the Reality of Time, published by Cambridge University Press in December 2014. It won the 2016 Prose Award, and its central argument is that the entire tradition of timeless law and physics is a mistake, not an approximation, not an idealization, a mistake. The universe is not the kind of thing that can be described by timeless mathematics. It is the kind of thing that produces mathematics and then outgrows it. At the Rubin Museum of Art in New York City on April 24, 2013, Smolin made the argument with unusual moral force. If I think the future's already written, he said, then the things that are most valuable about being human are illusions along with time. We still aspire to make choices in life. That is a precious part of our humanity. There's a loss of responsibility as well as a loss of human dignity. And this is where the scientific question becomes something more than an academic debate. Because what Smolin was really saying is that the question of whether time exists is not just a question about equations. It is a question about what kind of universe you are living in. And both answers are terrifying. If Barbour and Rovelli and the Page-Wootters mechanism are right, if the Wheeler-DeWitt equation is the truth, and time is nothing more than entanglement viewed from inside, then the block universe is real. The past is not gone. The future is not coming. They are both already there, encoded in a static wave function that does not change and has never changed and cannot change. Every decision you will ever make has already been made, not by you, by the wave function. Free will is not merely challenged by this picture. It is logically impossible. You are not making choices. You are a pattern of correlations in a frozen mathematical object, experiencing those correlations as a sequence of moments. But the sequence is an illusion. The moments are all equally real, all equally present, all equally fixed. You are not moving through time. Time is not moving through you. There is no movement, there is only structure. If Smolin is right, then time is real. But the laws of physics are not permanent. The ground beneath reality is shifting. The constants of nature that hold atoms together, that power nuclear fusion in stars, that determine the strength of gravity and the mass of the electron, are not eternal truths. They are temporary arrangements that emerged from a process and could change again. The universe is not a machine running on fixed rules. It is an evolving organism whose rules are part of the evolution. Nothing is guaranteed. Nothing is stable. The very physics that allows you to exist could be different in 1 billion years. Both options should keep you up at night. The field has not chosen between them. And here is what makes the situation even worse. It is not just two options. The philosophical landscape is more fragmented than that. Between Barbour's timeless Platonia and Smolin's evolving laws, there are dozens of intermediate positions, each with its own horrifying implications. There are physicists who believe time is real at the quantum level, but emergent at the cosmological level. There are physicists who believe time is real in one direction, but not the other. There are physicists who believe time exists, but is discrete, quantized into tiny Planck time steps of approximately 5.4 times 10 to the negative 44 seconds, so that the flow you experience is not smooth but stuttering, a film projected at an inconceivably high frame rate. There are physicists who believe that different branches of the many worlds wave function experience different times, so that the very concept of when is branch dependent. And there are physicists, a small but vocal minority, who believe the entire question is meaningless, that time is a word in human language that does not correspond to any definite physical concept. And that asking whether time is real is like asking whether Tuesday is blue. None of these positions are comfortable. Every one of them requires you to give up something you take for granted. And the fact that the smartest people working on the deepest equations in physics cannot agree on whether the most obvious feature of human experience is real should tell you something about the state of our understanding. We do not understand time. We have never understood time. And the most fundamental equation in physics suggests that the reason we do not understand it is that it is not there to be understood. Carlo Rovelli, born May 3rd, 1956, in Verona, Italy, working at the Centre de Physique Théorique at Aix-Marseille University, stands as the most eloquent voice on the timeless side. His career has been built on the problem of time. His 1991 paper, Time in Quantum Gravity and Hypothesis, published in Physical Review D, Volume 43, framed the question for a generation. His collaboration with the mathematician Alain Connan produced the thermal time hypothesis, published in Classical and Quantum Gravity, Volume 11, in 1994. The idea is striking. What we experience as the flow of time, they argued, is generated by the thermodynamic state of the system we are embedded in, extracted through a deep result in operator algebra theory called the Tomita-Takasaki theorem. Time does not flow because time is real. Time flows because we are ignorant of the full quantum state, and our ignorance generates a one-parameter flow that we experience as temporal evolution. Time is ignorance. That is Rovelli's phrase. He wrote it in his 2018 book, The Order of Time, and he meant it literally. His 2008 essay, Forget Time, which won first prize in the FQI Nature of Time essay competition, stated the position with a kind of clarity that only comes from decades of thinking about a single problem. The notion of time familiar to us may then be reconstructed in special physical situations, all within an approximation, as is the case for a number of familiar physical quantities that disappear when moving to a deeper level of description. For instance, the surface of a liquid disappears when going to the atomic level. Time for Rovelli is like the surface of a lake. It is real at the macroscopic level. You can see it, you can touch it, you can skip stones across it. But look closely enough, zoom in to the molecular level, and the surface disappears. There are only atoms, jostling and bouncing. The surface was never a thing. It was a pattern, and time, Rovelli argues, is the same kind of pattern, real enough at the human scale, non-existent at the fundamental one. And the thermal time hypothesis takes this further than most people realize, because what Rovelli and Kuchař were proposing is not just that time is emergent. They were proposing that the specific time you experience, the particular flow of moments that constitutes your conscious life, is determined by your thermodynamic state, not by the laws of physics, not by the geometry of space-time, by the specific way your molecules are arranged right now. Different arrangements would produce different flows. A different observer, embedded in the same timeless wave function, but in a different thermodynamic state, would experience a different time, not a different rate of time, a different time entirely, a different direction, a different set of correlations experienced as past and future. The time you experience is not a universal feature of reality. It is a parochial feature of your particular thermal situation. It is as local and as personal as body temperature. And Rovelli does not shy away from the existential implications. In The Order of Time, he wrote that the world is not a collection of things, but a collection of events. That the difference between a thing and an event is that a thing persists in time while an event occurs and is gone. And in a timeless universe, there are no things. There are only events, all laid out simultaneously, none more present than any other. Your childhood is an event. Your death is an event. And neither is more now than the other. The feeling that your childhood is past and your death is future is a feature of your thermodynamic state, not a feature of reality. He published the Italian edition, L'Ordine del Tempo, in 2017 through Adelphi. The English translation appeared the following year through Riverhead. It became a bestseller, and it contained the phrase that I think summarizes 60 years of the problem of time more honestly than anything else I have read. Time is ignorance. 2 words, the entire problem. If you knew the complete quantum state of the universe, if you could see the total wave function, you would see no time. You would see only correlations. Time is what you see when you do not have the full picture. Time is the cost of being a subsystem. The block universe idea, the idea that past, present, and future all exist simultaneously and that the flow of time is an illusion, goes back further than any of these physicists. Hermann Minkowski, in his September 21st, 1908 lecture at the 80th Assembly of German Natural Scientists and Physicians in Cologne declared that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Einstein resisted the idea at first, calling it superfluous learnedness. He came around, and on March 21st, 1955, 27 days before his own death on April 18th, Einstein wrote a letter to the family of his lifelong friend Michel Bessot, who had died on March 15th. The letter, preserved in the Albert Einstein Archives at the Hebrew University of Jerusalem, catalogue number 7-245, contains what is probably the most famous sentence in the philosophy of physics. In the original German, für uns gläubige Physiker hat die Scheidung zwischen Vergangenheit, Gegenwart und Zukunft nur die Bedeutung einer wenn auch hartnäckigen Illusion. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein was telling the Bessot family that their Michele was not gone, that the distinction between his being alive and his being dead was, according to the physics Einstein had spent his life developing, an illusion, a stubbornly persistent one, but an illusion nonetheless. The past, where Michel still lived and still worked through problems with Einstein at the patent office in Bern, was still there, still real, still as present as the grief the family was feeling, not as a metaphor, not as a comfort, as physics. He wrote those words knowing he was dying himself. And the H. Dieter Zeh, in the preface to his 1989 monograph, The Physical Basis of the Direction of Time, warned that the Einstein-Bessot letter is frequently misinterpreted as a statement about subjective experience. It is not. Einstein meant it as an endorsement of the block universe. He meant it literally. Whether that is comforting or horrifying depends entirely on which side of the debate you stand on. And there are serious voices on the other side. Tim Maudlin, a philosopher of physics at New York University, has argued that the direction of time is embedded so deeply into our language, our concepts, and our experience that it is impossible to expunge. His 2012 book, Philosophy of Physics, Space and Time, makes the case that the flow of time is not something we need to explain away. It is something we need to take seriously as a fundamental feature of reality. Maudlin is not simply defending common sense against esoteric physics. He is making a sophisticated philosophical argument that the block universe interpretation reads too much into the mathematics and too little into the phenomena. Craig Callender at UC San Diego, whose 2017 book, What Makes Time Special, won the 2018 Lakatos Award, took a different approach. He opened with the line, "Time is a big invisible thing that will kill you," and argued that the relationship between lived time, the time you experience, and physical time, the time in the equations, is far more complicated than either side of the debate acknowledges. Lived time and physical time, Callender argued, may be almost entirely distinct phenomena. The fact that the equations have no time does not necessarily mean your experience of time is an illusion. It may mean that your experience of time is tracking something real that the equations are not yet equipped to describe. And then there is George Ellis, the South African cosmologist who co-authored The Large-Scale Structure of Space-Time with Stephen Hawking in 1973. Working with Tony Rothman, Ellis proposed what they called the crystallizing block universe in a 2010 paper in the International Journal of Theoretical Physics, Volume 49. The idea is elegant and unsettling in its own way. The past is real. It is solid, determined, fixed. It is a block. But the future is not real. It does not exist yet. The present is the crystallization front, the boundary where indeterminate quantum possibilities collapse into definite outcomes and get added to the growing block. The block is real, but it is being built in real time. The past is concrete, the future is fog, and the present is the moment where fog becomes concrete. Ellis's model preserves what Smolin wants to save. The future is genuinely open. Choices matter. Free will has room. But it does so at a cost that few people discuss. It requires wave function collapse to be a real physical process, not merely an update of an observer's knowledge. And the question of whether wave function collapse is real is the measurement problem, which is arguably the other great unsolved crisis in the foundations of physics. The problem of time and the measurement problem are not separate puzzles. They are the same puzzle, viewed from different angles, and solving one may require solving the other. And here is where I think the institutional silence becomes most damning, because the fact that these two problems, the problem of time and the measurement problem, are connected has been known for decades, and yet they are studied by different communities, published in different journals, discussed at different conferences, funded by different grant programs. The physicists who work on quantum gravity rarely talk to the physicists who work on the foundations of quantum mechanics. The people trying to put time back into the equations rarely consult the people trying to figure out what measurement means. The problems are siloed. And the reason they are siloed is that combining them would force both communities to confront implications that neither is comfortable with. If time is an illusion and measurement collapses the wave function, then what is doing the collapsing if there is no time in which collapse can occur? If time is real and the wave function never collapses, then what generates the arrow of time, if not the irreversibility of collapse? Every combination of positions on these two problems produces a different picture of reality, and none of the pictures are reassuring. So where does this leave you? The equation has no time. The experimental evidence is consistent with time being a correlation rather than a fundamental parameter. The philosophical arguments on both sides are terrifying. The field cannot agree, and the two deepest problems in the foundations of physics are connected in ways that nobody wants to talk about publicly. And the data has been sitting there for decades. The Wheeler-DeWitt equation since 1967. The Page-Wootters mechanism since 1983. The Turin experiment since 2014. The Janus point since 2014. The theoretical rehabilitations since 2009. This is not new physics. This is not a recent discovery. This is a 60-year-old equation, a 40-year-old mechanism, and a 10-year-old experiment, all pointing in the same direction, all telling the same story. And you were never told. You were never told because the implication is too uncomfortable, because the physics community has no consensus on what to do about it, because saying time might not exist in a grant proposal is career suicide, even if the math supports it. Because textbooks are written by committees, and committees do not like sentences that end with, and we have no idea what this means for the nature of your conscious experience. The information was not hidden. It was published in the best journals. It was discussed at the most prestigious conferences, but it was never synthesized, never communicated to you. never translated from the language of Hamiltonian constraints and conditional probabilities into the language of what it means for the person sitting here, right now, listening to this, feeling time pass. This was published, verified, and then quietly ignored, not by conspiracy, by comfort, by the entirely human preference for questions that have answers over questions that threaten to dissolve the questioner. I want to return to Julian Barbour one more time, because his story did not end with the end of time, and the next chapter connects to something that even Barbour himself might not have anticipated. In 2014, the same year Moreva's photon experiment was published, Barbour and two collaborators, Tim Kozlowski and Flavio Mercati, published a paper in Physical Review Letters, Volume 113, Article 180-1100, titled Identification of a Gravitational Arrow of Time. What they showed is remarkable in its simplicity. Take a collection of particles interacting through gravity. Nothing exotic, no quantum fields, no string theory, just particles and Newtonian gravity. Simulate their dynamics, and what you find is that there is a single moment of minimum size, a point of maximum compression, where all the particles are closest together, from which complexity and structure grow in both temporal directions. Two arrows of time emerge from a single point, not because of special initial conditions, not because of some mysterious low-entropy Big Bang, not because God set the initial state of the universe with extraordinary precision, as a generic feature of gravitational dynamics. Run the simulation with random starting conditions. You get the same result. A Janus point, a moment of minimum complexity with two futures expanding outward in opposite directions. The implications are staggering. Boltzmann's past hypothesis, the assumption that the universe began in an extraordinarily unlikely low-entropy state, has been one of the deepest puzzles in physics since the 19th century. Why did the universe start with such improbable order? Barbour's answer is that it did not. The universe did not start. The Janus point is not a beginning. It is a midpoint. And the low entropy of the early universe is not improbable at all. It is the generic, typical, expected behavior of a gravitating system. The puzzle dissolves. The affiliation line on that Physical Review Letters paper, College Farm, South Newington, Banbury, Oxon Ox, 154JG, a farmhouse, published alongside papers from CERN, MIT, Stanford, the Institute for Advanced Study. And there, in the middle of them, a man working from a stone house next to a Norman church in rural Oxfordshire. And there is a connection here that I want to draw explicitly, because I do not think it has been emphasized enough. The Wheeler-DeWitt equation is also the starting point for the many worlds interpretation of quantum mechanics. DeWitt himself was the person who popularized many worlds. His 1970 Physics Today article, which I mentioned earlier, was the piece that brought Hugh Everett's relative state formulation to the attention of the broader physics community. And in the many worlds interpretation, the wave function of the universe never collapses. It simply evolves, splitting into branches whenever a quantum measurement occurs. But here is the critical point. In the Wheeler-DeWitt framework, the wave function of the universe does not evolve. It is static, h hat, psi equals 0. So what does many worlds look like in a timeless universe? The answer is that all the branches exist simultaneously, not sequentially, not one after another, all at once. Every possible outcome of every possible quantum event all encoded in the static wave function, all equally real, all equally present. The branching does not happen in time, because there is no time. The branching is a structural feature of the wave function, a pattern in the correlations, visible to internal observers as a sequence of events, but visible from the total state perspective as a frozen, infinitely complex mathematical object containing every possible history of every possible universe. Klaus Kiefer at the University of Cologne showed in the 1990s that if you perform a WKB approximation on the Wheeler-DeWitt equation, expanding the wave function in powers of the Planck mass, you recover a time-dependent Schrödinger equation for matter fields on a classical space-time background. Time emerges from the timeless equation through decoherence between branches. The branches cannot see each other. Within each branch, time appears to flow. But the total state, the state that contains all branches simultaneously, does not change. The many worlds interpretation and the Page-Wootters mechanism are not competing ideas. They are complementary aspects of the same timeless picture. What Kiefer showed is technically remarkable and philosophically devastating. The WKB approximation separates the wave function of the universe into a heavy part, the geometry of space, and a light part. Everything else, all the matter and radiation and fields that live on the geometry. The heavy part behaves approximately classically. It defines a classical space-time background. And on that background, the light part evolves according to the ordinary Schrödinger equation. Time appears because the matter fields are entangled with the geometry, and the geometry plays the role of the Page-Wootters clock. But the separation is approximate. It works only when the geometry is approximately classical, only when quantum gravitational effects are small, only when you're not looking too closely. Look closely enough, at scales near the Planck length of approximately 1.6 times 10 to the negative 35 meters, and the approximation breaks down. The background geometry becomes quantum. The separation between clock and system dissolves, and time disappears again, which means time is not just observer-dependent, as the Page-Wootters mechanism suggests. It is scale-dependent. Time exists at the macroscopic scale where you live. It does not exist at the Planck scale where quantum gravity operates. And somewhere between those two scales, somewhere in the vast hierarchy between 10 to the negative 35 meters and the meter-scale world of your daily experience, time switches on. It emerges. It crystallizes out of the timeless quantum foam like ice forming on a supercooled lake. And the process by which it emerges is decoherence, the same process that makes quantum superpositions invisible at the macroscopic scale, the same process that is responsible for the apparent classicality of the everyday world. Time and classicality are not separate features of reality. They are the same feature. The world looks classical and temporal for the same reason, because decoherence hides the timeless quantum substrate from view. You live in a decoherent branch. That is why you experience time. That is why the world looks classical. That is why you can read a clock and remember the past and anticipate the future. None of those abilities are features of the fundamental level of physics. They are features of your branch. They are features of the decoherent layer of reality that you have access to. Beneath that layer, at the level of the Wheeler-DeWitt equation, there is no time, no classicality, no branch, no you. There is only the wave function. And it equals zero. And that means the question is not just, does time exist? The question is, how many timeless branches of reality are you embedded in right now? And could you ever know? Barbour developed the Janus point idea into a full book. The Janus Point, A New Theory of Time, published by Basic Books on December 1st, 2020. Janus, the two-faced Roman god who looks simultaneously to the past and the future. The book is interlaced with Shakespeare sonnets and dedicated to his late wife Verena, who died of Alzheimer's, and to a recently deceased daughter. An 83-year-old man who had spent 60 years arguing that time does not exist, dedicating his life's work to the people whose time had run out. A man who says the past is not gone, that it is still there, still real, still present in the timeless structure of reality. And yet the people he dedicated the book to are gone from his experience. He cannot reach them. The correlations that would connect his current brain state to their living, breathing, laughing selves exist somewhere in the wave function, according to his own theory. But he cannot access them. He is trapped in his current, now, the same way you are trapped in yours. I still do not know what to do with that. When Physics World asked Barbour in 1999 what had kept him going all those years, he answered without hesitation, "The real thing that has kept me going all these years has been this very basic fact that time is just completely invisible. You cannot get your hands on it." Think about that for a moment. He is describing what amounts to a 60-year obsession with an absence. Not an object, not a phenomenon, an absence. The absence of time from the equations. The absence of time from the fundamental level of reality. He has spent more than half a century studying something that, according to his own theory, is not there. And the fact that it is not there, the fact that you cannot get your hands on it, is precisely what convinced him it was worth studying. There is something in that response that gets to the heart of what makes this story different from other stories about physics. Most physics stories are about discoveries. Someone found something. Someone built something. Someone measured something that was there. This story is about a loss. Something was expected to be there. Something that every human being experiences every second of every day. And when the equations were written down honestly, it was gone. The story of the Wheeler-DeWitt equation is not a story of discovery. It is a story of disappearance. And the people in the story, DeWitt, Wheeler, Barbour, Page, Wootters, Moreva, Rovelli, Smolin, are not explorers who found a new continent. They are investigators who showed up at the scene and discovered that the most important thing in the room was missing. And nobody can agree on whether it was stolen, whether it was never there to begin with, or whether they are all looking in the wrong room. When the Nautilus interviewer mentioned Carl Sagan's famous line that humans are how the universe knows itself, Barbour paused. "I have never read Carl Sagan," he said. Then, after a beat, he added, "I think Sagan's was a good hunch, a good hunch." The man who has spent 63 years arguing that time does not exist, who has watched his wife disappear into Alzheimer's and lost a daughter, who has never drawn a university salary, who published a paper in Physical Review Letters from a farmhouse, heard the suggestion that the universe knows itself through human consciousness and called it a good hunch. Because if the Page-Wootters mechanism is right, if time is what entanglement looks like from inside, then consciousness, human awareness, the subjective experience of being a thinking thing in a flowing present, is not a passive observer watching the universe go by. It is the mechanism by which the timeless wave function generates the appearance of time. It is the process by which the static becomes dynamic. It is the reading that makes the book feel like a story. You are not watching the universe. You are the universe's way of producing the sensation of watching. And the sensation includes time. Barbour is 89 years old. He is still active. He posted new material to his website, platonia.com, as recently as February 2026. He won the inaugural FQZ Essay Prize on the Nature of Time in 2008. He is published in the best journals in physics for 5 decades, and he still works from College Farm in the shadow of a Norman church, in a village where the population has not changed much since the Domesday Book. A man who spent his entire adult life chasing something invisible, not because he is confused, because the equation says what it says, because the experiment showed what it showed, because the math points where the math points, and because the fact that you feel time passing right now, the fact that this sentence feels like it is happening in the present, is not proof that time is real. It is proof that you are inside the entanglement and cannot see the whole picture. I want to come back to something personal, because I think this story deserves to end where it lives, not in the equations, not in the experiments, in you. You have been listening to this for some time now, and during that time, you have been doing something that you take completely for granted. You have been experiencing a sequence of moments. You heard my first sentence, and then you heard my second sentence, and then you heard my third. The word then in those sentences felt natural, obvious. Of course the sentences came in order. Of course one followed another. Of course there was a before and an after. That is what time does. That is what time is. But the Wheeler-DeWitt equation says there is no then. The Page-Wootters mechanism says the then you experienced is a correlation between your brain state and the state of the audio signal reaching your ears. And that correlation is structured in a way that looks like sequence from inside, but is static from outside. The Turin experiment showed that both descriptions, the flowing one and the frozen one, are simultaneously correct, and you have no way to determine which one is more fundamental, because determining that would require a perspective you cannot have. Think about what this means for something as basic as a decision. You decided to listen to this at some point earlier today, or yesterday, or whenever it was. You saw the title and you clicked. You made a choice. You felt the deliberation, the weighing of options, the moment of commitment. That feeling of choosing is one of the most basic features of being a conscious human being. And the block universe, the timeless picture that the Wheeler-DeWitt equation describes, says it was not a choice. Not because you are a robot, not because you are being controlled, but because the word choice implies that the future was open when you made the decision, that the outcome could have gone either way, that there was a genuine fork in the road. And in a timeless universe, there is no fork, there is no road. There is only a pattern of correlations in which one version of you is correlated with one set of circumstances, and another version of you is correlated with another, and both versions exist simultaneously, frozen in the wave function, each one experiencing what feels like a choice, but is actually a structural feature of a static mathematical object. That is what the physics says. And I want to be clear that this is not a fringe interpretation. This is the standard textbook reading of what the Wheeler-DeWitt equation implies about free will. It is not that free will is difficult to reconcile with physics. It is that the most fundamental equation in physics describes a universe in which the concept of choosing is incoherent. A choice requires time. It requires a before the decision state and an after the decision state and a process that connects them. And the equation says there is no process. There is no before and after. There is only the total state equal to zero, containing all correlations at once. Smolin understood this. That is why he called the elimination of time dangerous. Not intellectually dangerous, morally dangerous. Because if people believe it, if they internalize the idea that their choices are not real, that the future is already written, that nothing they do can change anything because everything is already determined in a frozen wave function, then something is lost. Something human, something that matters. And Smolin is not wrong to worry about that. But the equation does not care about his worry. It says what it says. And here is the part of this that I personally find most difficult to sit with. Your experience of the present moment, the feeling of now, is the one thing you cannot doubt. Descartes tried to doubt everything and landed on, I think, therefore I am. But even that formulation presupposes time. It presupposes that the thinking is happening, that the I is present, that the act of doubting is occurring in a moment that is real. The Wheeler-DeWitt equation challenges even that. It does not say you do not exist. It says the moment in which you exist is not a moment. It is a correlation, and the correlation does not require a flow or a present or a now to exist. It just requires the wave function to have a certain structure, which it does, which it has always had, which it will always have, because always is the wrong word, because always implies duration, and duration implies time, and time is the thing the equation says is not there. You see the problem. You cannot even describe the situation without using temporal language. Every verb you use, every tense, every word like was or is or will be, smuggles in the assumption of time. The English language was not designed to describe a timeless universe. No human language was. And that may be the deepest reason why this result feels so wrong when you hear it. Not because the physics is incorrect, but because the physics is describing something that human cognition was not built to comprehend. You evolved in a world where time is the most salient feature of the environment. Your brain is a prediction machine, optimized over millions of years of natural selection to anticipate what comes next. Take away next, and the brain has nothing to work with. It is a compass in a world without magnetic north. You are trapped inside your own experience of time the way a character in a novel is trapped inside the story. The character experiences events in sequence. The character feels the tension of not knowing what comes next. But the book is already written. Every page exists simultaneously. The story is a spatial object, ink on paper, all of it present at once. And the illusion of temporal flow is created by the act of reading, by moving your eyes from left to right, from one page to the next. The character cannot step outside the book to check whether the story is still being written or whether it was finished long ago. And neither can you. That analogy is imperfect. All analogies for this are imperfect. Because the thing I am trying to describe is, by definition, something you cannot experience directly. You cannot experience timelessness from inside time any more than you can see the back of your own head with your own eyes. The limitation is not technological, it is structural. It is built into what you are. The Wheeler-DeWitt equation was scribbled in an airport in 1965. Published in 1967, ignored, feared, cursed, and fought over for 6 decades. The man who wrote it called it that damned equation and died of cancer in 2004 without ever reconciling what it said with what he experienced every morning when he woke up and put on his shoes and walked to his office at the University of Texas and watched the clock on the wall tick forward second by second, the way clocks do, the way clocks have always done, the way clocks will always do unless the equation is right, in which case the clock is not ticking. It never ticked. It is entangled with you, and the entanglement looks like ticking, and the looking is all there is. DeWitt spent the last years of his life in Austin, working with his wife, Cecile DeWitt Moret, who was herself a distinguished physicist. They had married in 1951. They had 4 daughters, and when DeWitt died on September 23, 2004, the obituaries described his contributions to the quantization of gravity, his role in popularizing the many worlds interpretation, his work on quantum field theory and curved spacetime. What the obituaries did not describe, because it is not the kind of thing obituaries describe, is the private experience of a man who had derived an equation that says the universe does not change, and then spent 37 years watching his children grow up, watching his wife age, watching his own body decline, watching the seasons turn and the clock tick, and the world evolve around him in every conceivable way, while the equation on his blackboard continued to say none of it was happening. That is a particular kind of loneliness. The loneliness of knowing something about reality that reality will not confirm or deny. And it is the same loneliness Barbour describes, the same loneliness Page and Wootters must have felt when their paper was shelved, the same loneliness Moreva must have felt when she watched her entangled photons simultaneously evolve and not evolve, and knew that the result, however elegant, however precise, however real, would be called merely an illustration and filed under interesting but inconclusive. The loneliness of knowing something about time that time itself cannot tell you. You are sitting here, you feel the present moment. You feel seconds passing. You remember what I said at the beginning, and you anticipate that I am about to stop talking. That feeling, that flow, that sense of being carried forward on an invisible current is the most intimate and undeniable fact of your existence. It is more certain than anything you can see or touch or measure. It is the one experience that requires no external confirmation. You know you are in time the way you know you are conscious, immediately, undeniably, without argument. And the most fundamental equation in physics, the only equation that describes the quantum state of everything there is, says it is not happening. The equation does not care which interpretation you prefer. It does not care whether you find the block universe comforting or terrifying. It does not care about free will or entropy or Augustine's confusion or Einstein's grief or Barbour's farmhouse or Smolin's anger or your life. H hat psi equals 0. Nothing changes. Nothing has ever changed, and the fact that it feels like it is changing is the deepest clue you will ever get about what you are. You are not a being moving through time. You are a correlation in a wave function that the equation says is frozen. And the flow you feel, the now you inhabit, the present tense in which you exist, is what it looks like from inside a system that cannot see itself. Bryce DeWitt was right to call it that damned equation, not because it is ugly, not because it is ill-defined, because it is telling you something about the nature of your own experience that you are not equipped to hear. Something the math has been saying since 1967. Something a man in a farmhouse has been saying since 1963. Something the photons in Turin confirmed in 2014. You are not in time. Time is in you. And the equation that describes the universe you are made of says that the you who is hearing this, and the you who started listening, and the you who will stop are not three versions of the same person connected by a river of time. They are three correlations in a static wave function, 3 points in a structure that does not move, 3 patterns in something that the most fundamental equation in physics insists has never changed, cannot change, and will never change. And you will never be able to prove it wrong. Not because the evidence is hidden, but because proving it wrong would require a view from outside the universe. And there is no outside. There is only the inside. There is only the entanglement. There is only the zero.